So these are kind of, I hope that gave you kind of a flavor of the kind of devices and the kind of effects we typically see on aircraft. But there are actually other devices that I think we need to mention because they're quite interesting. Number one, and this is something probably people sometimes confuse, is spoilers. So spoilers here, these are basically these plates you guys can see when you're landing. So they just suddenly come up, okay? And so they're upper surface flaps, okay? And what they do is they destroy lift by causing flow separation. So they go up and they cause a lot of flow separation. That really reduces the lift in your aircraft because remember, you're trying to land. You don't want too much lift. They're also useful for increasing the rate of descent. So you obviously don't want to take ages trying to land. So it's useful to land quickly. Also, because of flow separation, you will find that the drag increases. But really, what we're trying to do is to really kills the lift off. So these are the spoilers. So they kind of spoil the lift. However, air brakes are slightly different. Air brakes is, we focus on increasing the drag rather than reducing lift, okay? So this is how they work. One focuses on lift and killing lift, the other one focuses on increasing the drag. And for example, we have an air brake here on this picture here, okay? And of course, as it creates a lot of drag, you slow down the aircraft so that you can, for example, land. So I just try to show you those so you actually, in a way, they're trying to do similar things, but the function, the principle is different. One of them kills off the lift, the other one creates more drag. Just if you guys think about, I mean, in terms of the second picture, for example, I'm sure you've all seen the space shuttle landing. You saw that they have the parachute, right? So that is basically effectively an air brake. And the parachute, as you pull it working, it will create a lot of drag to slow down the space shuttle and help it to land, right? So, suction and blowing. These are kind of difficult technologies to implement on aircraft, to be honest. So I'll be honest there and say there have been mainly academic work and research work, but to really implement them in aircraft, they're incredibly expensive, incredibly difficult to maintain. But they are useful at least to think about. So suction and blowing, really here the focus is on the boundary layer. We want to have effects on boundary layer. In terms of suction, you just suck the fluid, and blowing is you blow the fluid. So in terms of suction, we can achieve that using what we call suction holes. So on the wing of aircraft, we create tiny, tiny holes, okay, along the chord of the aircraft, for example, or specific sections of the wing. And typically, they're on the size is about 60 micrometer. They're quite small. And what they do is they remove the lower boundary, the lower region of the boundary layer, and keep the other one which has more kinetic energy, and therefore the boundary layer will have more kinetic energy in a way, and therefore it will not separate as easily. So this is in a way similar to leading edge device effects. Blowing, it does exactly the same thing. So what we do here is, again, from a blowing hole, we inject high energy fluid tangential to the surface along the boundary layer to give it more energy, and therefore it will sustain it and separate it for a larger angle of attack or a lot more operational range. Typically, the slot size or the hole size is 1.5 millimeters. But I have to say, as I said, there have only been some experimental aircraft try to demonstrate these things. They have demonstrated it, but it's on a commercial level to have it. I'm not aware of any operational aircraft in life where actually there is suction and blowing. It's just incredibly expensive. That's all, really. Blown flaps, what they use is a very similar concept to suction and blowing, really. But here they just use the flow from the engine, the jet engine exhaust in particular, again to energize the boundary layer. And apparently, been reported that the CL can be as high as 4.5 to 5. Okay, so you get, it's not a very clear picture, but you guys can see this is the trailing edge flap, yeah, here, and you got the exhaust flow from the engine, and we kind of try to direct it to go over the trailing edge flap. That energizes the boundary layer of that flap, which allows it to deflect more, which gives you more camber and gives you more lift. Okay. One thing is of interest is vortex generators. Anyone seen these on planes? Planes wings, if you came across, anyone seen this? No? Have you? Who's seen them? On cars, yeah, we have them on cars. Very good. Actually, I should have put a slide to show. Actually, we have kind of those devices on racing cars as well. But sorry about that, forgot. Yeah, we can have them on cars. Anyway, so they're very small, kind of small vanes that you actually basically distribute along the wing. They're typically triangular or rectangular in section, but they're very small, typically on the size of the boundary layer, so they're very, very tiny. But what they do, again, they work on the concept of energizing the boundary layer. So as you guys shown here in this picture here, once you have this vortex here, vortex generator, sorry, what happens is that a vortex, literally, a vortex of high energy is created along this kind of street of vortex generators, and that energizes the boundary layer. So you're adding kinetic energy by, on purpose, putting those things along the wing, which gives you these kind of high energy vortex flows, okay? Which again, they allow the boundary layer of the wing to remain attached for a higher angle of attack, and that will give you more lift. So I'm just saying here, next time you fly, maybe look very carefully, you will see one of these. But these are, yeah, a lot of aircraft commercially, they have these vortex generators, so they're definitely used. So let's just summarize with some challenges of high lift systems or high lift devices. We already mentioned the problem of complexity and the related problem of increased failure rate of components. So really, people have for a while now been trying to think, how can we reduce the complexity of the design of these components? And there is a lot of work going on. Of course, the fact that you have a lot of components means you have to think about maintenance. And for an airliner, that's a lot of money to pay to make sure all the components are working all the time. So there is kind of a drive to reduce what we call, to reduce the number count of components in system. And if you reduce the components, of course, you will reduce the weight automatically. And of course, we know the more weight you reduce, the more people and luggage and crew and stuff you can put on the aircraft, so you make more money. That's fine. So people, of course, have been looking at ways of using materials that are strong enough but light in weight. And of course, I talked about noise is very important around airports, and regulations. If you guys read the history of regulations, obviously they're becoming stricter in terms of noise. And anyone designing an aircraft in the next 10 or 15 years, they probably will have to, I'm sure they will face stronger regulation in terms of the noise generated, which forces people then to think about every little thing on an aircraft that is a noise generator and try to reduce that, including, of course, high lift devices. The problem is, with all these problems, they are a necessity. We can't fly an aircraft without those high lift devices, really, the way we want, because we want to go fast and we want to take as many people as possible and their luggage and stuff. So far, so the kind of, I don't want to call them a necessary evil, but we can't live without them. You can't fly without high lift devices. You can't land the takeoff without them. It's impossible, the way we want anyway. But it's good to try to think about some of these issues and at least how can we improve them. And the reason I'm saying that is maybe some of you in the future get into maybe work on high lift devices and try to tackle some of these issues, because there are real issues, they're not superficial things. So, in conclusion, I can say that high lift device is a very complex topic. Honestly, I'm just giving you a flavor of the things you can encounter. And you guys have seen there are many possible solutions in terms of leading edge devices, trailing edge devices, and their combination. And for each aircraft, there will be an optimized kind of deployment of those systems that gives you the best in terms of lift and drag. In terms of research, I can tell you that there's a lot of work that has been done, of course, on high lift devices and how to improve lift. In terms of concepts, it's actually quite well studied, but in terms of the issues to sort out, like noise and weight and so forth, there are actually still a lot of work to be done. And I've shown you that vortex generators and blown flaps and like suction and blowing, of course, they have also the potential to increase the lift further. So in terms of future devices, I just thought I'd share some thoughts with you. For example, a lot of people, of course, these days talking about morphing wings. Conrad, morphing wings? Yes. So you created a morphing wing on a small aircraft? Yeah. Is it working? It works. Yeah. It morphs. Okay. Very good. So the morphing really is about, well, doing what the high lift devices do, but without some of those issues, particularly in terms of weight and in terms of noise. And basically what we want is to close the gap. So you get the same effect, but kind of reduce the effect of gaps or have no gaps if possible at all. But this is really what it is closing those gaps to reduce the aerodynamic noise. So yeah, morphing wings and morphing trailing edge flaps, morphing leading edge flaps is definitely one of the research topics at the moment. And it tries to basically, in the future, everyone is asking the question, can we get rid of complex high-lift devices we have currently on aircraft and replace them completely with morphing systems that overcome some of those issues I mentioned? I think it's possible, but it definitely will take a long time. Not because we're not able to do it, I think because aircraft manufacturers like Airbus and Boeing, they're very careful, and rightly so to be honest, to just introduce any technology on their aircraft. And of course that technology will take years and years for testing and certification. So it's not an easy process. You know, designing an aircraft typically takes 10 to 15 years, even more. So putting those technologies, I don't think is going to be in the near future, I don't think, but at least there's potential for that. And of course here at UE, some of us have been working on morphing, and actually we did some work even with undergraduate students. And yeah, so morphing is quite an interesting topic we're looking at all the time.